Yeah, yeah. Now it is live. It is live. Then you can start introducing the speaker. No problem. Yeah,
Okay, it is live now. Yeah.
yeah, it's live.
Okay, fine.
Before that, you wanted to check this PPT.
Yeah, PPT also we can. Anup, you can just open your PPT. Yeah,
Yes, sir.
it is live now.
Sir, is it visible, sir?
Yeah, yeah, it is visible. No problem. Yeah, Dr. Prasad, we can continue. No issues. No issues.
Right. Okay. Thank you. So, good evening to all the esteemed members of the Ocean Society of India, ladies and gentlemen. The Ocean Society of India conducts this invited talk as part of the webinar series held once in every month. And this talk is arranged from eminent scientists, engineers, academic professionals working in the broad areas of atmospheric and ocean sciences, ocean engineering and technology. This webinar is mainly targeted for students, researchers, scientists, engineers, and working professionals in the broader area of atmospheric oceanic sciences, ocean engineering technology, and allied disciplines with a motive to impart and improve the knowledge that benefits the OSA community. So I request all the members to actively participate and get involved in all the lectures under the webinar series that is held every month. So on behalf of the Ocean Society of India, it is my proud privilege today to welcome Anup Kumar Mandal from the Space Application Center, Ahmedabad, for the invited talk. So Anup, actually, I'll give a brief introduction about Anup. Anup actually has done his 1 minute just. Yes, he has done his BSc in Physics honors from the University of Calcutta in 2013, and thereafter his M.Sc in Physics from the Ramakrishna Mission, Vivekananda University, Calcutta. So he has secured a first class with a university gold medal in the year 2015. And thereafter he has joined as a scientist engineer SC at Space Application Center in March 2017. And from January 2021 till date, he's a scientist engineer SD at Space Application Center. So the areas actually of interest are on storm surge modeling, application of satellite data in oceanic processes, tropical cyclones, internal waves, induced mixing. And Anup Mandal actually has published several research articles in reputed journals and several conference proceedings. So with this brief introduction, so it is my privilege to kindly invite Anup Kumar Mandal to deliver the talk. Now the participants actually requested that the question and answers will be attended after completing the talk. And the questions actually can be messaged in the chat box. So thank you. So Anup, you can just start your presentation. Yeah.
Thank you so much, sir, for the introduction, and I thank you, Bhaskaran sir, and the organizers of OSI monthly webinar series for giving me the opportunity to deliver a lecture on importance of storm surge and associated coastal inundation estimation during cyclones along the east coast of India, and it is based on a satellite data perspective. So I will start the presentation now, and is my presentation visible to all? So
yeah, it is visible. It is visible.
okay, sir. So I will put in this way. So currently I am posted in Space Application Center, and I am working in the Oceanic Sciences Division. And so here I will be talking about the storm surges. So let me just recall that in last few years, the most severe cyclones that happened in the North Indian Ocean. So basically, in the left-hand side, what I see is the super cyclonic storm KR. So this was the first super cyclone after Gonu, 2007, with a sustained wind of 240 kilometers per hour. And in the right hand side, what you see is the super cyclone Amphan. You can see the size of the cyclone is very huge, and this is actually our INSAT 3D image. The brightness temperature is shown from PIR1 channel, and the date is, this one is for October 2019, and right hand side you can see it is for May 2020. And the images are obtained from mosgag.gov.in. So these severe cyclones, when they make landfall, and they basically generate huge waves, which are known as storm surges. So the water elevation, abnormal water elevation due to the cyclones, and that I will be talking about next. So today's lecture is following way. So first I will be talking about what is my motivation for storm surge forecasting. And then I will be talking about very briefly about the basics of storm surge generation and its propagation, and the factors that influence storm surges. Now, what is the role of satellite data in storm surge prediction or estimation? And there I'm talking about numerical models that I use for simulation of total water relating to the cyclones. And then I will be sharing some latest results that I am carrying out in past few years, and also my ongoing research. And then I'll be showing some forecasting results of surge in inundation. Then I'll conclude, and then follow the. So first I will go to the motivation. So you can see this map. This I have taken from NOAA. This is a Westpac archive data between 1980 and 2017. And these are the cyclones that form over different basins. So the basically Indian Ocean accounts for 7% of the global tropical cyclones, and it is estimated that storm surge induced coastal inundation accounts for around 90% mortality. And also the frequency of cyclones from this paper suggests that it is 5 times higher in the global than in the M.Sc. Of course, in recent years, the number is also increasing in the M.Sc as well. And tropical cyclone along the Bay of Bengal accounts for 60% of the deaths due to storm surge. And because of this sea level change due to the global warming, this has a massive increase in flood risk in the coastal region. That is, you can find from these brackets. So here we have shown two different scales. One is the Saffir-Simpson scale, and another is our scale provided by Indian Meteorological Department. So a cyclone is categorized in this. First, let's say I take this IMD scale. So it forms into a depression, then subsequently it forms into deep depression, then into a cyclonic storm. And if it further intensifies, then it forms a severe cyclone or very severe, and in some cases super cyclonic storm that I showed in my first slide. So the category is different based on the Saffir-Simpson scale. So here you can see it is tropical depression, then tropical storm. Then it is several categories based on the sustained wind speed. Let's say category 1, 2, 3, 4, and 5. Also, you can see there is this knots, and they have also defined using kilometer per hour. So these are the basic about the cyclogenesis. Now let us talk about what happens when the cyclone makes a landfall. So storm surge is an abnormal rise of water that is generated by a storm over and above the predicted astronomical time. So if the cyclone is not present, we have the tide level. But when the cyclone is making a landfall, that time the water will pile up near to the coast, and we have this abnormal rise of water that we call storm surge. So in this figure, you can see I have a mean sea level here, and there is a normal high tide, let's say of 2 feet. And now suppose due to the cyclone, the surge height is 15 meters. So total height due to the tide and storm surge is 15 plus 2, so that is 17. That is termed as storm tide. So storm tide is the water level due to the combination of storm surge and astronomical tide both. Now it requires a reference level, which is in this case a mean sea level. Now this storm surge, if it is high, then it can also penetrate into the inland from the coastline, which we call inundation. So due to the increased amount of number of cyclones in the Bay of Bengal and Arabian Sea, so generation and simulation or you say forecasting of these storm surges is absolutely very important. And this is what I am involved in Space Acquisition Center. So, but what causes these storm surges? So basically, this is the diagram. The first diagram, you can see the vertical section of a cyclone. So here we have a eye, and then this is the storm direction towards the coast. Now there are two components which actually includes the storm surge. One is the pressure driven surge, another is the wind driven surge. But the pressure driven surge, the contribution is minimum. The majority contribution comes from the wind driven surge. And hence in the models, the primary forcing comes from the wind fields. Now, when it is in the open ocean or in deep waters, so due to the cyclonic circulation, the wind circulation, so there is a current also in the ocean, vertical circulation, as it is shown here. So in deep water, there is nothing that you can disturb for the circulation, and there is no such pileup of water, and there is very little indication of storm surge. But once it approaches the coast or the mainland or the shallower water, so the circulation it becomes disrupted by the ocean bottom. So the water has nowhere to go except the into the land. So it will pile up near to the coast and it generates the storm surges. And basically it happens when the winds are blowing onshore. So highest surge tends to occur near to the radius of maximum wind. Where you have the wind speed as the maximum winds, there the surge will develop, the maximum surge will be. So which is shown in this diagram. So this diagram I have taken from NOAA. So here the cyclone, this propulsion direction is represented by this green line, and here let's say the winds are onshore, the direction is onshore. So therefore the storm surge is actually developed in this type of location. Next, let us talk about the total water elevation. So total water elevation is a combination of tides and the waves and also the freshwater input. So in the Bay of Bengal, the east coast, we have east coast of India. So we already know that we have a semi-diurnal tide. And for the Arabian Sea, let's say the west coast, we know that it is a mixed tide. So the tide levels are always there. Let's say the cyclone makes a landfall when the tide is high. So then in that time, the water elevation or the storm surge, it will have the highest impact because the total water elevation will be a sum, right? And if the cyclone makes landfall during a low tide, then the total water elevation will be less because due to this value in this case. Then because of the breaking of the waves, so water is also piled up. So that also contributes and that has to be taken account. And a huge amount of rainfall is associated due to the cyclone. So that's freshwater also through the river inlets, it goes into the coast, and once it is towards the ocean, so especially it will be the water level also gets increased in the delta river delta region and in the bay areas. So the total water elevation is basically the collection of all these four factors: the storm surge due to the cyclone, the tides, the waves, and freshwater input. So the factors that influence storm surge. So first of all, and most important, is the cyclone intensity or the wind speed. So needless to say, if the strong winds will produce higher surge, as the wind is the primary forcing. Then the size of the cyclone is also important because a larger cyclone will produce a higher surge. And there are two reasons for this, because the area of the cyclone is large. So it is actually pushing a lot of water, basically larger amount of water towards the ocean. And second, it will have a larger amount of time to propagate to the land. Then the storm forward speed. So generally, open coast, there is a fast moving storm will produce a higher surge. Then there are many research papers on the angle of approach to the coast. Suppose it is approaching perpendicular to the coast. So that time the storm surge will be much higher than when the storm is actually moving parallel to the coast or it is moving at an opposite. Also, another important aspect is the shape of the coastline. So let's say the cyclone makes landfall in a concave coastline as opposite to the convex coastline. So surge will be higher if it is the shape of the coastline is concave. Also, it depends on the width and slope of the ocean bottom. So as we can see, the geometry of the domain, basically the depth or the bathymetry is very important aspect when we talk about the simulation of storm surge, and also the wind speed. So how accurate is your input wind forcing when you are trying to generate or simulate storm surge? Now, what is the importance of satellite data? So we can use satellite data in various ways. So first, I will be talking about in the inputs of the estimating of storm surge. So as I said, the geometry of the domain is very important. Basically, the topography of the bathymetry. So the generation of storm surge or the accuracy of the storm surge that we have generated is basically dependent on the bathymetry and topography that we are using. Now, globally, we have SRT and DEM. Now, SRT and DEM is basically shuttle ladder topographic mission that is provided by NASA. So we have a 30-meter resolution data globally, which is available. And here in this figure, in this slide, I have marked in this green color. So those are actually the ISRO satellites. So let's say for digital elevation model, we have our Cartosat series in ISRO. So likewise, let's say satellite derived winds. So WindSat is a global data set. Suppose ASCAT is advanced spectrometer, and we have our SCATSat-1 that is provided by ISRO. And our latest ISRO satellite is US-06, also known as OceanSat-3. So OceanSat-3 is basically, I think it was launched in November 2022. And then these goes as inputs. Then we can also use for sensitivity experiments and for more even fine tuning the storm surges by using the satellite derived land use band cover data, which is a short form of LULC. So now there are global data sets that you can use for the LULC. So MODIS data set is there, which has a special resolution of 500 meters. Likewise, Sentinel-2, which is provided by ESA, it has a special resolution of 10 meters. And ISRO has its own land use land cover data, which is the name of ResourceSat satellite. So these data sets can be utilized as an input to the storm surge model. And as per the validation part, we can use the water level measurements from altimeter. So JSON series that gives us the altimeter data, basically the sea surface height or the absolute dynamic topography that we can use as a validation if the pass is available during the cyclone. Also, Saral, that was Saral Nautica, that mission is provided by ISRO. And the SWOT that was launched in last year, December 2022. So surface SWOT stands for surface water and ocean topography mission. So this actually SWOT provides us the SWOT measurements of the water level. So this can also be used if we have the data during a cyclone. And also, if we have a pass before the cyclone and after the cyclone from a satellite of, let's say, synthetic aperture radar. So this SAR stands for synthetic aperture radar. So we can actually make that what was the inundation from a SAR image if we have two passes before and after the cyclone. So different SAR scenes can be used for basically making out that how much inundation actually happened. So this is a measurement of actual inundation. So we have this Sentinel-1 series again provided by ESA, and ISRO has its own SAR, latest SAR satellite in the name of US-04. This was launched in February 2022. And also we have upcoming NISR mission, which can be further utilized for this validation part. So here I'm not talking about the conventional validation. Let's say we have a tide gauge data, so that we can also use for validation of the water levels, right? And also we can use buoy derived winds. So buoy has these wind measurements, and we can use the buoy winds to validate our wind speed also. So, and suppose we do not have a bathymetry, and then we have to use the model data. But here I have written, you can ask why this bathymetry is written. So, in the latest few papers, we have seen that bathymetry can also be estimated from a SAR unit. So, that bathymetry can also be used if the accuracy is okay. Then that bathymetry from a SAR scene or optical scene can be also utilized further into the as an input of the geometry, which goes further into the storm surge model. So this is the overview of different satellite data that are useful for storm surge study. And in the green color, what you see is actually the satellites provided by ISRO. So in the next slide, I'll be talking about the simulation of total water movement. So we are using state-of-the-art hydrodynamic model, which is known as advanced circulation model. So advanced circulation model short form is ADSR. And this model is actually coupled with the simulating waves nearshore model, which is the short form as SWAN model. So, I will be talking about ADSR model just in a minute. But what are the gap areas that I found when I started the work is that the major lacuna is in the accurate representation of the geometry. So suppose the geometry or the bathymetry is actually changing day by day. So we need to use the updated bathymetry. So in this case, you can use the latest DANE or latest bathymetry from latest DANE you can use from a satellite, and the bathymetry we can get from the model or ship measurements or even the in-ship. And also we have to be very careful so that the geometry actually resolves very small features. Let's say small creeks and river inlets and also small islands. So these actually act as feeders which carries the storm surge into the inlet. And hence to achieve the realistic coastal inundation, we need a very high resolution and very accurate representation of the coastal geometry. So how we achieve that? In our case, I'll be talking just after a few slides. Now, what about this? What is the basic idea of this advanced circulation model? Is that so it actually solves the circulation equations in 2D and 3D, and it uses flexible unstructured triangular grid. Okay, and so because of this unstructured grid, we can actually have a handle over the resolution. So we can use this methodology to make our mesh or our geometry, which has a very high resolution near to the coast, and we can relax or may lower our resolution when we go to the open ocean. So this is the very type, so that the number of nodes is actually or number of points where we are doing the simulation is optimum. Otherwise, if we use, let's say, structured mesh or a gridded mesh, then the number of grid points will be much higher. So we need higher resources to run the model. So this was actually provided by or developed by Lutwich Junior in 1992, and basically it solves the momentum, particularly integrated momentum and generalized wave continuity equation to obtain the current fields and the surface water elevation. And ADSR actually uses the wet dry scheme. So suppose due to the equilibrium between the friction and the water level, so a triangular element may become wet due to the wind speed and the friction. So that time we can say that it is wet. Similarly, suppose the water level is the depth. Basically, you can define a depth that at this depth, the grid point will be wet, and below this depth, the grid point will be dry. So these wet dry scheme is actually inbuilt in ADSR, and this is very useful when we are talking about inundation, or basically the inland propagation of the salt water. And now this is the methodology. So suppose I am doing a hindcasting. I already have the cyclone track data from IMD base provided by IMD base track. So in that case, generally we use the parametric Gillespie wind speed, which was developed by originally by Gillespie, then it was modified by Rao et al. 2018. So we are using this modified Gillespie wind speed. So it basically generates our cyclonic wind based on the IMD's base track data. So IMD base track data has this cyclone position for different dates, and then other information also. Let's say what is the pressure drop at that particular instant of time, and also what is the wind speed at that point. So based on this information, we can generate the cyclonic wind, basically a two-dimensional wind at each node. And for forecasting, I am using our in-house developed. So it is developed in SAP. So some other person, they are working in the WRF model. So I'm using the WRF model output in 5 kilometer spatial resolution for generating the forecasting of the water level due to the cyclonic storm. So I will start from here. So here, all the data you see, it is basically the bathymetry or the topography. So let us start from one by one. So ALTM DEM is a airborne measured DEM that was provided by M.Sc. And it is very highly accurate digital information model of the land parts and also the low-lying areas. And I have used for my study this Cartosat 2 derived DEM, and some location where these two datasets were not available, there you can basically use this TM just to fill the gap. Then this Hydrographic Office, they have this bathymetric chart data that we can use, and also the EUCO 2-minute resolution data that was also modified data. So that modified data is used to generate the geometry using a software which is known as surface water modeling software. This is the short form SMS 12.2. So here the mesh is generated, or you can say the geometry is prepared based on all different DEM data or a bathymetry data set. So a merged bathymetry and topographic data is first prepared here, and then this merged data is actually used to generate the mesh. Then the mesh is further utilized with the wind information and the tide information. So here you can see the geometry is given. So basically the geometry is nothing but a lat long and the depth of that line. Okay. So then we are using the wind from either for hindcasting we are using this parametric Gillespie wind, and for forecasting we are using wind from WRF along with the tide also. So this goes to the coupled advanced circulation model coupled with SWAM. And because of that, the output will be, so this is our model output, the total water level as a combination of tide, storm surges, and the effect of wind waves. And when it propagates over the land, then we have a coastal inundation. So this is the entire framework of simulating the total water inundation as well as coastal inundation during a cyclone. Now, how can we get the storm surge? So basically, we can switch off this wind part and we can simulate tides also during cyclone. So that will give me the tide level. Then we can subtract the tide level from the total water elevation, and then we can get the surge residual. So this we term as surge residual. So that I haven't shown here, but suppose I want to calculate the storm surge, that can be done in this way. Just subtract the tide part from the total water elevation. So here I have shown the different data set that we are using. So first is airborne leader DEM. So it has a very high accurate spatial resolution, so 1 meter resolution. And then Cartosat 2 DEM that we have in spatial resolution of 10 meter. Then as I mentioned, TM DMA has a spatial resolution of 30 meter. So these three are the topography data sets. And then these two I am using for the bathymetry data. So national hydrographic orbit chart data, so here, and then the ETOPO2, which is the 2-minute data. So you can see, after we have prepared the domain using this merged data set, the geometry is very well represented. Let's say this is the Krishna River region. So all the river inlets and these delta regions, the fine structures basically. So these are actually very well represented by this data set. Also the Chilka Lake. So it is a known common problem in some modern data sets that the lakes or the inland, these water bodies that are not well represented. But for Chilka Lake, we have used the measurements by Chilka Development Authority, CDA. So we got the data and we have used the data along with these available data. So Chilka Lake also we can visualize. So this is a very good, well represented domain or the geometry that we can further use into the storm surge model. Now, using the merged data set, topography and bathymetry data set, we have prepared the 100-meter resolution finite element triangular mesh. So the mesh structure is shown here. So this is the bathymetry and topography which is shown here with the major station, and the zoom version is shown here. So you can see near to the coast, the resolution is very fine as it is represented by the dense values of these triangular elements, and as we go away, the resolution is actually decreasing. It is becoming higher. So we have this total, the resolution is 100 meter near to the coast, suppose here in this region, the maximum resolution. And then when we go to the open ocean, there we can relax the resolution. So there we have chosen around the 18 kilometers, so open ocean region. And this is the land boundary. So it is represented in this color here. Okay. So these actually represents our land boundary. So we have taken this land boundary so that the storm surge will not propagate beyond this point. So that's how it is taken. So this is the 10-meter topographic contour we have chosen. So now we have carried out the basically this storm surge simulation for our cyclonic cases. So these cyclones were chosen. So Thane 2011, then Foilin 2013, then Hudhud in 2014, then followed by Varda and Titli in 2018. So apart from Titli, the other cyclones are used to simulate the total water level in the hillcast level. And then for based on this study, then we use this further for the forecast. So these are actually results from a work that was published in 2020 by me, and it was with the collaboration with IIT Delhi. So we did this work and this was published. So I am just presenting you the results. So means how much accurate we got. We simulate the total water level or the storm surges or the inundation. So as I mentioned, 4 cyclones, Thane, Foilin, Hudhud and Varda were selected for the HIMCA simulation. And then 50 cyclone we use WRF model forecast tool for forecasting the total water elevation or storm surge. So this is our WRF model domain. So it has a listed domain. So domain 1 has a resolution of 25 kilometers and domain 2 has a resolution of 25 kilometers. So basically our mesh domain is like this, which falls into the domain 2. So that's why the 5 kilometer resolution we were used for the forecasting purpose. Now I will show some results from the simulation that we carried out. So first, before we go to the cyclone part, we must validate and check whether the model is able to resolve the tidal signal correctly or not. So the phase matching during before the occurrence of the cyclone is very important, so that if the phase is not matching, then the model will not be able to generate the storm surges or total water elevation properly. So we validated this tidal water elevations using the invoice type gauge data. For 3 stations I am showing here. So it was for Eminode station in the top panel, then followed by the Paradip, and third one is for Visakhapatnam. So these are the results. So we have a very good correlation running between 0.97 or 0.98 and low RMSE values between the model water level and observed water level from the tide gauge data. So I'm very thankful to INCOES that they provided this tide gauge data to carry out the simulation. Now, in all these cases, the standard index is less than 30%. That means that our model tide is very useful so that it can be used operationally with a good reasonable scale. So you can see this paper for further reference. Now, because this model is able to generate the tides very well, so can it generate the storm surges? That is the question that I will show next. So here I am showing the beamcasting simulation result. So as it is written, so the first result is for Thane cyclone, followed by Phylum cyclone in 2013, then Hodo. So I have chosen very strong cyclones for this work, and we carried out the simulation using the modified Lesniewski scheme, as I mentioned, which was developed by Rao et al. 2018. And you can see in each of these test cases, suppose I take the case of Thane cyclone. So we validated both. So storm tide basically means the tide plus our storm surge. So this is our model tide in this red color in both these figures, in all the figures, and the observed level tide levels is actually shown in the this black color. So if I subtract the model tide from this both, then we can get the observed surge residual as well as the model surge residual, which is shown here. And basically the statistics of the validations are shown in this table. So we can see the validation results are very good, and it varies between 0.86 to 0.98, and RMSE is also it is acceptable for all these four cases. So since we are able to generate the Beamcast result very well, so we went one step ahead and we tried this very much well configured model for the forecasting purpose. So as I mentioned in my earlier slide, that these four cases were for Beamcasting simulation, and the Tipi cyclone we used other forcing, WRF model forecast for forecasting purpose. So let us go to that. So before that, we have some special plot for the coastal inundation also. So this is actually a special plot of maximum surface water elevation due to Phylum cyclone, and this is for Hudud cyclone. You can see this inundation near to the Ganjam district and some other district for Hudud cyclone. And the extent, inland extent also is mentioned here. And the track is the IMD west. So now this is the result of the forecast. So this is actually the storm tide due to the forecast generated on October 10, 2018. So this is the WRF forecast, so which is extracted from the WRF model forecast data. And these different boxes are actually zoomed in. So this is actually a zoomed image of this portion, where the elevation is also shown, and also you can see the coastal inundation district. So now, as I mentioned, that we can use the satellite derived SAR data. So SAR data, we can get this observed inundation also. So we also carried out that, and here in the left hand side, I am showing that the forecast track was slightly different from the IMD based track, which we got later. So there was a difference of 20 kilometers between this WRF model forecast and the IMD based track data. And now on this right hand side, we have used in this paper the RadarSat-2 derived SAR data for validating our this inundation data. So what you see in this right side, so the blue these polygons, they actually show us the inland inundation due to the cyclone, and which actually excludes the permanent water bodies. And we have the observed inundation, which is actually marked in this black polygons. So the result around 60%, 65% of the inundated area is observed to overlap with the data that was observed by RadarSat-2 satellite. So RadarSat-2 is a SAR satellite, synthetic aperture radar, which is the Canadian Space Agency. They actually provide the data set. So, and also the area that we observe is that around 35.4 square kilometer that we observed from the RadarSat data, and around 30 kilometer was of 30 square kilometer was observed in the model. But here there are two things that we have to remember, because this is a forecast. So because of that we can get the underestimation. Also, we can see there was a difference between the track also. So this is highly important, that we have to improve the track of the forecast so that we can get the actual forecast. So I will go ahead and talk about another work that I am carrying out. So another work that I am currently carried out is using satellite derived units into the storm surge model. And let us see. And basically, we wanted to see whether the satellite datasets are useful for generating the generation of storm surges, and how can we improve the satellite data so that the generation of storm surges becomes even the accuracy becomes even more. So here, the validation of the wind speed from different satellites I have shown here. So first of all, let us go one by one. This left, this figure, first figure. So this windsat and then StatSat, then this red lines is represented the MoES data, then the NCEP GFS data, and also the merged satellite, which is the system. So what is windsat? Windsat is the polarimetric radiometer, and this gives us the wind speed as well as the wind direction. So it is first of its kind, and this data can be used. So it has several modes. Let's say all weather mode data is very useful. However, there is a valid range for each of these sensors. So we have to use very carefully the one. And the StatSat, this ISRO satellite, we have this data set that I have shown here. And then the measurements from the MoES, basically the instrument measurements that is shown in the red color. Now CCMP stands for cross-calibrated multi-platform data set. So it is actually a merged product of all available satellite data. So what are the components of this CCMP wind? So I can name a few. Basically, it merges winds from spectrometer as well as radiometer. So for spectrometer, let's say it takes QuickScat, ASCAT, and then for radiometers, it takes, as I mentioned, windsat and also GMI, TMI, EMSRE. All these satellites are taken care. So satellite has this pass, and these data sets are prepared based on the merged satellite work. But the query is that even if we merge all the satellites, we are not able to cover the entire globe. So the background field that is taken in the CCMP is the NCEP GFS analysis field. So NCEP GFS analysis field goes as the background field to this system. But you can see the difference when we try to validate the cyclonic winds or wind fields during a cyclone with respect to MoES. So the first one is the wind speed from CCMP versus MoES, and second one is the wind speed from GFS, which is the background of this CCMP data. So correlation coefficient is similar, but what about the RMSE? That RMSE is slightly lower in case of CCMP, as it is 2.66 meter per second, and for NCEP GFS it is around 4 meter per second. So one important observation what we get from this figure, the first figure, is that a single satellite alone, is windsat or StatSat, is not good enough that you can use in a model, because the data available is very small. So when you have the cyclone pass over a swath, then you can use the data. But for model, in order to use this data into the model, we need the data at equal time interval. Let's say we need a 6-hourly data or a 3-hourly data, that kind of. So we cannot use a single data set from a single satellite. So our data from a single satellite is not useful for storm surges because of the non-availability of the data. So that's why in our study we chose to use merged satellite product, which is the CCMP derived winds. So what is the impact of these CCMP winds on the storm surge generation? That I will come in my subsequent slides. So before that, I just wanted to show a spatial plot and how the difference that we can see from the CCMTV and its background, which is the NCEP GFS movie. So this is for Fani cyclone, and this is around 12 hours before landfall. Then it is 6 hours before landfall, and this is 6 hours after landfall. So when the cyclone is actually in the ocean, there we have this kind of wind distribution, and then when it is very close or after the landfall, then we have this kind of difference. So top panel, the wind speed is from this clock calibrated multi-platform, which is mass satellite product, and in the bottom panel, it is the background speed. So there are some differences. We can plot the difference also, but one important observation that I see from here is that after the cyclone makes the landfall, just after the landfall here, you can see the wind speed in the ocean is more than it is in the land. So this is basically due to the friction of the land. That's why the wind speed is reduced. So this fact that the wind speed is actually low into the land, this can also be addressed in our future work through the land use and cover data. Okay, and here we see for this test case basically, I have mentioned here just the wind speed from IMD data and the wind speed from this our CCMP data and GFS. So now I will go and let's say into the next slide. So here I have shown the spatial distribution of maximum wind from our model. So we have carried out this study for using 5 different wind fields. So first one is the wind speed due to maximum wind speed due to JTWC based. So we can use in the model, and it goes into the model through a parametric wind scheme known as generalized asymmetric Holland model scheme. So that is shown here. So wind speed is like this. And if we use the modified Jelesniewski scheme based on the IMD base track, as I mentioned earlier, so what is the model of wind? That spatial distribution is shown here in the B this figure. Now, what about the satellite wind? The satellite derived cross-calibrated multi-platform wind that is shown in the C figure. And if we use only the background field GFS, that is the 6-hourly winds, that is shown in D. So both CCMP and GFS, they are 6-hourly winds that we have to remember. Now further, we actually constructed a synthetic wind of which is GFS 3-hourly. So here we merged both GFS 6-hourly winds with GFS 3-hourly forecast, just to generate a synthetic. So that if we wanted to check also that whether there is a improvement if we increase the temporal resolution from 6 hours to 3 hours, that we wanted to see. So then these are the observations from this study that we found that the maximum wind decrease from this order, from JTWC, then IMD, then GFS, then CCM. And of course, the cyclone size is larger in CCMP and NCEP GFS because the resolution is poor. So spatial resolution in the NCEP GFS data or CCMP data is 25 kilometers. So that's why the cyclone size, basically 1 pixel is equal to 25 kilometers. And then that's why the cyclone size is much higher. So these are actually this scenario, these are the limitations that we get this much. So what we can do for our future actions. So that's what we need to do. And what happens if we want to try to validate the surge residual? That also I wanted to show. So here we can see the surge residual validation is shown for this Fani cyclone, and it was located around 110 kilometers away from the right side of the land. So all the models, the correlation is very close to each other. So this is a Taylor diagram of this line plot. So the statistical information from the line plot is actually represented in this Taylor diagram, as you see here. So what is this Taylor? I will take just 1 or 2 minutes just to explain this Taylor diagram. So this Taylor diagram actually visually shows the statistical parameters. So in this axis here, the numbers represent the correlation between the two data. So suppose the observation has a correlation 1, obviously, so it is shown in this star. And then let's say JTWC. So here it is represented by this purple line, and here it is represented by this purple dot. So it has a correlation around just below 0.9. So that's why the point is represented. And now these concentric circles from this point here, this actually represents the root mean square error between the observation and each model. And the x-axis actually represents the standard deviation. So our observation has some standard deviation and other model data also. Let's say we use the JPWC wind or the IMG wind or the CCMP or GPS. So different data set will have different standard deviation that is shown in this x-axis. So this is the statistical representation, and if I talk about the whether we are able to see the improvement in the storm surge if we use the 3-hourly data, I say yes. Now yes, because the peak surge will actually improve by around 10% if we use the 3-hourly GFS wind instead of 6-hourly. But now let us say if we go slightly farther away from the cyclone, what happens in that case? So what happens to these validations that I wanted to show in my next slide here. So this is the surge residual validation for Tifli cyclone at the Vishakhapatnam tide gauge station. Again, we used the data provided by Invoice, and this time the tide gauge location was located around 180 kilometers away from the location of the landfall. Now here comes the challenge for the parametric winds. So you see, the parametric winds are designed in such a way so that the cyclonic wind distribution is very much well represented inside the influence of the cyclone. But as we go away from the influence of the cyclone, the wind intensity or the wind speed falls very much. And then the wind, because of the reduction in the wind speed, we are not able to capture the generation of the storm surge. So here, in the observation, we can see a storm surge of about more than 0.5 meters, where at Vishakhapatnam station. But if we use the parametric winds from JTWC base track data or IMD base track data, we are not able to resolve these positive values. We are actually, in fact, getting negative values here. That's why in the correlation plot, this JTWC and modified Jellinsky scheme is coming somewhere around here, between -0.2 and -0.4. However, in this case, the satellite derived wind or the 3-hourly GFS winds, those perform better. At least they give some kind of a positive surge where the observation is also around plus 0.5 meters, the received. So this is actually the advantage of the satellite data, that we can use, that the wind direction is somewhat better represented for the surge development. So because the storm surge here, the residual is positive, the winds must be onshore. That's why the surge developed. So we further checked that why these models, the surge was negative, in order to just to understand why, whether the winds were onshore or whether it was offshore. So that I am showing in the next slide. Okay, so as I mentioned, for this study we have used 5 different wings. So one is our based on the JTWC data, the first one. The second one is our GFS in modified GFS data. Third one is CCNP, then GFS 6 hour, and the last one is GFS 3 hour. So as we can see that if you observe here at this point, the validation was done somewhere here, Vishakhapatnam, for Tittli cyclone. Now, if you observe, the winds were actually offshore. You see the direction it is directing away from the coast. So winds were actually offshore at this point. So the time was around 3 UTC. And if we see from the CCMP data or the GFS data, it is again somewhat parallel to the shoreline, or parallel to the coast. But as we see that surge actually developed around 0.5 meters, so it must be onshore. So that we further check from our StatSat SWAT data. So there we had a pass, fortunately, after 50 minutes. So as you can see here, the winds were slightly onshore. That's why we got this surge. So what I conclude from this study is that even in today's framework, we do not have the satellite data that can give realistic storm surge. So the resolution should be at least 1 hour, then it can produce the realistic surge. Because the time period for the storm surge development is around that time. So you can see if it was around less than 1 hour or around 1 hour, then you can resolve the direction properly. But because the winds were around 6 hours, or here it was 3 hours, so it still it could not resolve the direction. As in this case, it was somewhat parallel to the coast, but actual observation was actually towards the coast or the onshore wind. So next I'll be showing some of the results that that are generated. So this is basically during a cyclone, we generate these storm surge forecasts, and it is available in this link. You can visit this link, mosdag.gov.in/Scorpio, to view all the files. So this is for the latest cyclone that happened just few months back, for Biparjoy cyclone in the Gujarat. So the track of the cyclone is shown, and also the surge visible. So here the storm tide, the total water deviation was first calculated, and it was subtracted, tide was subtracted, and the result is shown here. So you can see near to the Nalia district, somewhere here, the storm surge is highest. So these forecasts are for different days. So the forecasts are generated daily. So from 12 of June 2023, then 13, then 14, and then yeah. And another, so these are also available from MOSTAC site plus Scorpio. So this is the coastal inundation map. We also share these maps. So this part is a zoomed in image where we can see the inundations also. So the basically this work we are doing so that incorporating the satellite winds, whether we can improve the storm surge or inundation forecast. And if we find the improvement pretty much, then it can be, or it can be shared with the operational agencies. So I will be in future looking for some collaboration with the operational agencies, let's say MPOES and IMD, and I'm open to any collaborative work based on this kind of thing, the assimilation of satellite data. So now I'll conclude that in this study we have used different satellite derived digital elevation model, and we have used satellite derived winds, and also we have used the satellite derived basically SAR images to validate the inundation also. So these are the application of satellite data we can use first to generate the storm surge and then to validate the storm surges also. And we can, in future, we are thinking about using this land use land cover data for further improvement of the inundation forecast, and also how to improve the forecast, whether it has some impact or not, that we want to study by assimilating the altimeter data. So altimeter gives us basically the absolute dynamic topography. So during a cyclone, if we can assimilate that data and whether it has an impact on the total water elevation or coastal elevation, that is going to carry out in near future. So I will conclude here, and I am very thankful to Professor Prasad Bhaskaran to give me the opportunity, and I also thank the organizers of OSI webinar series, and I would like to sincerely thank our director of Space Application Center, Deputy Director of IPSA, and Group Director. And I'm also grateful to our head, Oceanic Sciences Division, for his guidance and his support and encouragement. So, and I finally also thank all the listeners. And these are the references that I have used this work and for further study. Thank you. And now I'm open to any questions.
Yeah. So thank you, Anup. It is a very interesting and very informative talk.
Thank you, sir.
You had given a very good overview on the importance of satellite data in the perspective of storm surge and inundation during cyclones for the different coast of India. So you started your presentation by giving a very brief overview about cyclogenesis. Then you touched upon coastal vulnerability and the basics of storm surge, importance of storm tide, and what are the causes of the storm surge, wherein you have described about the vertical section of cyclones and how the cyclones basically can impact the total water level elevation near to the coast during the time of landfall. And you also stressed upon the importance of the storm surge and the total water level elevation, which is a nonlinear combination of the storm surge, tides, waves, and also the freshwater input. Then after that, you also covered the aspects on the factors that influences the storm surge, specifically on cyclone intensity, the cyclone size, the forward translation speed, angle of approach, the coastline shape, width and slope of the ocean bottom, and what are the inputs which are essential prerequisites for the storm surge modeling. You actually very elaborately described about the role of topography and the bathymetry for the enhancement of surges in the nearshore regions, and also it is very informative description about the satellite derived winds and also the satellite derived land use, land cover changes. And then you talked about the validation aspects of the data, and you have also actually shown the simulations of the total water level elevation and the methodology behind it. It was very clearly described, and you applied for different case studies like for the Chilka Lake Lagoon. You have shown actually the AdCirc grid and high resolution grid, which is about 100 meters near to the coastline. And the same AdCirc model, which was configured for the Indian coast, was validated. I mean to say the tide validation was done for Ennore, different locations like Ennore, Paradeep, and Visakhapatnam. And you also described about the coastal inundation that happened due to Titli cyclone and the importance of the modified Jalesnia and ski winds for the Fani cyclone. And in fact, actually, the entire presentation was very well articulated, and I'm sure actually that the researchers working on this area will find it very useful and also very informative, because this topic is basically of interest with the number of tropical cyclones as well as the threat of storm surges that the Indian coast is basically facing today. And in the event of a climate change, we know that the intensity of tropical cyclones are also seen to increase. There are variations in the severe cyclones, the frequency of severe cyclones, especially in the Arabian Sea part, which is going to be a topic of interest in the coming future. And I'm very sure that actually this particular study, what Anup and your team is working on, it is very useful, and it has got a lot of socio-economic consequences, at least in the context of climate change. But at the same time, there are so many gap areas, and there are knowledge gaps in the subject, as what you have pointed out. So you have actually very well articulated your presentation by also mentioning the limitations of the study, and also the highlighting on the 1 hour time which is required in the satellite information for effective storm surge studies. So this is an overall overview of your presentation, and I find it very interesting, and I think the others also support me in saying that this presentation is really good, because it has covered almost all the aspects of the storm surge and different types of case studies that has been carried out for the coastline of India. Now, I think there are no in the chat box. I do not find any questions that has been posted, but I have a couple of questions only because of lack of time. I will restrict it to just 2 questions actually. You mentioned about the freshwater input in the total water level elevation.
Yes, sir.
So this freshwater input, actually, how do you plan to integrate in the total water level elevation? Because the AdCirc model basically gives the water level elevation that is due to the storm surge, the tides, as well as the wave induced effects or the radiation stress.
Yes,
Suppose you have a lot of rainfall or something that is happening in the area where the rainfall is also contributing to the flooding.
Yes, sir.
So how actually you plan for looking into this aspect?
So we can have, if we have the data of the river discharge during
Right.
during the rain and during the cyclone, that suppose we have a historical data of the river discharge, and we can have the output of the basically the rain also. So if we have this information, so based on the, so river is coming downstream.
Yeah.
And our storm surge is propagating upstream.
Right.
So there is one study that I have seen carried out by again Professor Reddy Rao. So that there we can integrate using some external coupling. So the river water is coming towards the ocean, and storm surge is propagating towards the land. So
Right.
based on these 2 inputs and the flow of these water masses, we
Yeah.
can have an external coupling, and we can get the total combination combined
Okay.
effect of
Yeah.
these 2.
Okay. So basically, that is I think yeah, that is fine. And suppose we have this landfall which is far away from the river. For example, if the cyclone has not, the landfall of the cyclone is not close to the river, it is very far away. Let us say it is about 200-300 kilometers away from the river. So in that area, there will be a lot of rainfall.
There will be a lot of rainfall. So there we need a very high resolution and accurate representation of the precipitation.
Okay.
And this much precipitation is happening.
Hmm.
So basically, because there is no river,
Yeah.
so the amount of water that is going towards the ocean
Yeah.
will be less than if the river was present. Now if we can calculate the basically the amount of rainfall at this location, so that can be used to generate the combined inundation map due to the cyclone as well as the rainfall. So there also we can generate a combined basically.
Okay, fine. And in your presentation, you have mentioned about the satellite derived LULC, and you have actually highlighted about MODIS Sentinel-2 and the resource sat.
Yes, sir.
So what is the resolution, actually the highest resolution that we can get for this LULC?
Sir, to best of my knowledge, if you are looking for a global data, so that is from Sentinel-2. Sentinel-2 gives us a 10-meter resolution. Global data set that is available from 2017 to 2022.
Okay, so it is
So
10 meters resolution.
It is 10 meters, sir. So basically, visible band they are operating. So it is a visible channel they are operating. So it is provided by ESA and it has a resolution of 10 meters.
Right, right. That is okay. That is good. That is very good.
And sir, this resolution of the data is also 10 meters. This LUS, land use land cover data, is also 10 meters.
Okay.
And then the next, I think, is the resource set. But unfortunately, the resource set is for only for our Indian
Okay.
Indian mainland. It is not available for the Sundarban that goes into the Bangladesh and then followed by Myanmar and those portions. So it is limited to our this Indian coastline this area. And then we have this MoES data, which is coastal resolution, which is 500 meters.
Okay. And you also mentioned about this for inundation studies, the inland inundation from the SAR images for the wherein you have highlighted about the Sentinel-1, EOS-4, and NISAR, which is upcoming.
Yes, sir.
So will the coverage be there actually? What is the repetitive period actually? Like we get the data from this?
Sir, I will explain.
Yeah.
So for now, currently we have this Sentinel-1 and EOS-04 data, which is operational. So Sentinel-1, the visit time is 10 days. And the EOS-04, we have the repetitivity of 18 days for if we want to use the MRS data, that is the medium resolution scan-SAR mode. That data. So the repetitivity is 18 days for EOS-04. So it is very recently launched. So these two satellites we have, and EOS-04 both the combination of Sentinel-1 and NISAR is it is planned in 2024. January 2024, the launch is proposed in January 2024. I think the data will get after 3 or 4 months.
Okay.
So, sir, for upcoming cyclones or in the future, we can use the combination of these three because individually the repetitivity is less, let's say 18 days or 10 days. But if we use the data as a combination, because all are SAR sensors. So sir, this Sentinel is working in the C band, and EOS-04 also it is working in the C band, and NISAR it is working in a L band and S band.
Okay, okay,
So
that is fine.
different channels, but if we use a combination, then definitely we'll have the coverage, at least few scenes during the cycle.
Yeah, that will be really good. That will be really useful also because we need to have a better coverage.
Yes, sir.
So that it can be used for evacuation purpose as well as for the emergency response and all. It will be very useful.
Yes, sir. Definitely there will be. If we use as a combination, so then it will be even increase the temporal visit time.
Yeah. Okay, I think there are no more questions. I don't see any questions in the chat box. And
Prasad, I have one question to the speaker.
Okay, there's one question. Yeah.
Actually, I'm trying to understand, rather I'm wondering it. We are having huge amount of data. We are processing large amount of data sets, correct? So are going to use any kind of machine learning, deep learning concept to reduce the traditional way of processing or modeling the data sets?
Sir, currently I am not doing it, but in future, yes, of course, I am also planning to do it that way. That's a very good suggestion, sir. Actually, currently in my talk, I have not included any machine learning related things, but these are also becoming popular day by day as it reduces our processing time and also means it is based on the algorithm. So that is actually very good. So I'm also in future, I'm also planning to develop based on the artificial or AI based.
So that is the case, then we should think about collaborative way of working with things. So basically, MoES has separate vertical for IIT Pune. We have separate vertical for machine learning, AI machine learning, separate vertical for particularly for developing different kind of approach, how we can reduce the modelings, speed and computational concept, all the things.
Yeah.
So we can think about it. See, now it is the ministry has taken as a very serious concern. And another thing is 2047. What you call whatever the proposed we are giving the plan. After 10 years, after 5 years, then 2047. What could be our stand as from Indian point of view, science point of view? So what we need, what we are going to do that. Most of the people will be retired. By the time So, sir, how we are going to do that? So, what is our stand, particularly science or modeling or other things? So, just we can think about it because I mean, significantly we have a lot of time how we can do the things.
Yeah.
Sir,
More or less, I mean, ISRO and the ministry, I mean, our ministry has huge amount of data. So, we have to think in that direction.
sir, how can I contact you means for collaboration and
Yeah, I can send you my details. I mean, I can send you my details. No problem.
sir, my email is I have not written, but my email is just sir Anup Mandal 92 at the rate
Yeah.
gmail.com.
I have your details. I have your contact details. I can get it. That's not a problem.
Okay, sir. Okay, sir. Please send me. I mean, actually, I am also looking for a collaborative work in this field.
Yeah.
It will be very nice, sir.
Yeah.
We can plan
Yeah.
with MoES and
Okay, thank you.
Thank you. Thank you. So thank you, Anup Mandal. So on behalf of the Ocean Society of India, I thank you for the wonderful talk. And I believe actually that this talk will have a lot of viewers in the YouTube, because since it is recorded in the YouTube, you'll have many people actually watching maybe in the night time, because whenever they get time, actually they see this presentation. So I believe actually this will have a very good impact on the new generations actually that are working on the area of storm surges and coastal flooding. So thank you very much once again. Yeah.
thank you, sir. Thank you for Ocean Society organizers also. And I
Thank you.
hope it will be helpful to the.
Yes, yes, yeah, definitely.
Thank you,
Thank you.
sir.